good morning, everyone. First, I'd like to thank the conference organizers for inviting me. At SNS, we love to get up and talk about what we believe to be a very unique application of RF, and that is the acceleration of charged particles. Okay, so why do accelerators need high-power RF in the first place? So we're gonna actually, this talk will answer this two-part question, right? Why do we use high-power RF, and how does SNS use it? So to start, we're going to talk a little bit about some accelerator basics. I understand this is the last day of the conference. I understand there might have been a lot of fun last night that involved karaoke, so I promise you it will be very light. Only 2 formulas, 0 math. Then when we get through that, and you kind of have a little bit of an accelerator physics background, we'll talk about exactly how SNS puts RF to use. We'll talk about our ion source. We actually use 27 megahertz. The gentleman asked about use for 27 megahertz. We can use that to actually make plasma. We will then talk about the cavity types. So at SNS, you can imagine we have a multitude of cavity types. We're really going to focus only on the accelerating cavities. We do have other RF cavities, I should say, that actually bunch the beam, and we'll touch on those, but I won't spend a lot of time on them. Then we'll talk about our high-power RF sources. We are heavily tube-based, so if there's anyone in the room that still uses, triodes, tetrodes, knows what a Klystron is, you're in the right place. That's what we're going to talk about. I just saw a hand. It was much, much less than 50%, I have to say. Then we'll talk about how we control those. We do have a nice little control loop, FPGA-based control loop that we'll talk about. Finally, we'll talk about the ring, a little bit more about beam physics, the ring specifically, how we accumulate our protons, and how we use those protons to ultimately make neutrons for material science. Okay, so everyone in the room, I think, understands there are 2 ways to accelerate, or 2 types rather, of electric fields, of E fields. We have electrostatic, and we have time varying. So let's talk about electrostatic for just a second, and why it is we do not use a DC field to accelerate charged particle beams really anymore. So what you see here is a picture of the Hollifield facility at Oak Ridge National Lab. In its day, it was the world's leading electrostatic accelerator. It's advertised as a 25 megavolt accelerator. I think it actually went north of 30 megavolts, and I think it set a world record at around 32 megavolts. It's a tandem accelerator, so what that means is ions start at the bottom, they are accelerated to the top. At the top, they do some charge exchange, turn them from negative to positive, and then accelerate them the other way. That way they can get the most energy into the beam using the DC. So why is it, how do these things work? And why is it we don't use them really anymore? So you could think of it really, as you can imagine, it's like stacking batteries, right? You have these high voltage modules, you reference them to each other, you have to stack them up to come up with these really high potentials, and eventually it gets very difficult to keep standing that voltage off, right? You get arcs, you get breakdown, and the practical limit is about 30 megavolts. So you can see that Holyfield is about as good as it got when it came to DC acceleration. And to give everyone a little point of context, so at SNS, the hydrogen ion that we accelerate, we actually get that. We get it. Its final energy level rather is 1.3 giga electron volts. So to do that with DC, you would need 10 to the 9 volts. I mean, you can imagine that's really practically impossible to do. So we use time varying or RF fields. So here's a picture. I'll get into the details of this in a few slides. What you see here is actually a picture of our drift tube Linac. And so the way that RF field works, so we take advantage of resonance, right? We use the resonance of the cavity to ring up a really high voltage in a gap. And it's tough to tell from that picture, but what you see there are tubes, drift tubes, and in between each drift tube is a small gap. We're talking literally centimeters, and we can set up a very high electric field, and when the particles pass through that field, they gain energy. And so you can imagine you can string a lot of these together in a really small amount of space and really get a lot of energy into a beam, and that's why, that's why we use RF instead of DC for particle acceleration. All right, here's the first of 2 formulas, the Lorentz force equation. I'm sure many of you are already familiar with it. I'll be very brief. It's basically describes the force a charged particle feels from an electromagnetic field, right? So we're going to talk a lot about the large capital E there, the E field. I'll spend a little time on the B field right now. The B field we use in an accelerator to combat space charge. So we focus the beam with it, steer the beam with it. The E field obviously is what we use to accelerate or bunch the beam. So I mentioned resonant cavities on the previous slide. So resonant cavities, you can imagine, also make a pretty good filter, right? We designed them to oscillate really at a very narrow band, more or less a single frequency. And the timing, the arrival of those charged particles in that resonant cavity is very, very crucial, as you might imagine. So the graphic down there that you see on the bottom of the page basically describes that. So what we want to do is we want those particles to arrive at the sort of, if you think of the RF as a sine wave, right? You want to think that the particles, if we want to accelerate them, want to arrive on the wave, on the rising wave, so that they get pushed. If they come in the wrong phase, they get decelerated. We have what we call beam loss, which means the beam scatters everywhere. You release radiation, bad things happen, and we don't get to do the fun science on the far end of the accelerator. So it's very important. The timing is actually a very important part of this whole equation as well. So RF cavity basics. Again, everyone in the room, I think, understands resonant frequency. So with a cavity, it's no different, right? It's just a big metal can. You shape that can, you change the volume of that can, and you can affect things like the inductance of the can, you can affect the capacitance of the can, and what you get is a resonant cavity. And so it's really easy to model. We just use a simple RLC model to start. You have a resistance, which basically is heat loss, right? You're bombarding this can with RF, you're going to get current in there, you're going to get heat loss. That's the resistance. The walls also count as the inductor, right? Or can be modeled rather as the inductor. And then the gap that I talked about, we model that as a capacitor. And the gap is probably the most important part, right? Because that's where we're going to put energy into the beam. And so I get this question a lot. How do you determine how much RF power a cavity needs? Well, really, it's simple. It's two things. How much you're going to dissipate in the cavity. Most importantly, how much does the beam need? How much energy do you want to add to that beam in that particular gap? That's how we determine how much RF power we need. And you'll see here in a few slides, at SNS we're talking about kilowatts and megawatts of RF power. So here is sort of a schematic overview of the SNS, and I'm going to briefly go through the different RF systems that we have here on this slide, but we use a variety of RF cavities. And you can see energy levels here, beam energy levels on this graph, and we'll come back to these throughout the talk. But we have on the far left-hand side the normal conducting, so it's just room temperature. And then where everything turns blue, that's actually cryogenic temperatures. And those are superconducting cavities. And you can see right away, we get a large energy gain from about 190 MeV to 1.3 giga electron volts there at the very end of those superconducting cavities. So most of our energy gain is there. But just briefly, I'll go through all the RF systems. So on the front end, where we make our ions, where we start our beam acceleration, we have 8 RF systems. Those include some solid state amplifiers that you see there on the right, and then we have a tetrode-based amplifier that we use to actually ignite the ion source. This is an RFQ. I'll talk about this in a minute, but the RFQ stands for Radiofrequency Quadrupole. From the RFQ, then we go into our MEBIT cavities. MEBIT stands for Medium Energy Beam Transport. So the MEBIT cavities actually do not accelerate the beam. They actually just clean it up. And they make these bunches that we'll talk about sort of at the end of the presentation. They make the bunches very clean, and that's important when we go to accumulate in the ring at the very end of the accelerator. So then, once we exit the MEBIT, we enter into the true acceleration starts. Now, drift tube Linac that I just mentioned a few minutes ago, and then our couple cavity Linac, and I'll give you some more details on those here in a couple of slides. And then finally, the bulk of our RF systems reside again in our superconducting Linac, and that is also where we get the majority of our energy gain. And I would be remiss if I did not mention the ring. Again, we'll come back to it, but here there's also no acceleration. The ring consists of 4 tetrode-based RF cavities, and they actually simply clean up the bunches and combat space charge as we accumulate more and more protons in that ring you see there on the far right. So I guess the main point that I want to make here is that we string together literally hundreds of these cavities using 131 RF systems to power them, and we pulse these cavities 5.2 million times per day, 60 times a second, 24/7, to make the 1.3 GeV beam. Okay, so first we have to have an ion to accelerate. We heard a lot about the ionosphere and bouncing radio waves off of it. Now we're going to talk about how we use RF to make an ion. So what you see here is a schematic view of our ion source. And the way it works is, first, I kind of lied. I said we use 27 megahertz. We are starting to use 27 megahertz. On the actual production machine, we still use 13.5 megahertz, 600 watts CW to ignite our plasma. So we have a low intensity plasma. We then pulse that with 2 megahertz at 80 kilowatts to really get things going. And I should mention too, and I failed to, that this is actually hydrogen gas that we're turning into a plasma. And what happens is, and I don't have a laser pointer and I apologize, on the far right-hand side of that schematic, well, I should say this. We actually bias this whole thing at negative 65 kV, okay? So what happens is, as these hydrogen ions interact with a cesium collar that I think you might be able to see, I can't quite read my own graphic here, but we have a cesium collar that the hydrogen interacts with. We heat that collar up, cesium gives off electrons to the hydrogen very easily. It becomes a negatively charged ion, and then the 65 kV quite literally pushes the ions out into the accelerator. And so why do we use H-? I get that question a lot. That's a very good question. I'll explain more at the very end. It becomes, again, important when we go to accumulate protons in the ring. If you want to think ahead a little bit, think opposite charges attract. Okay, I went backwards, sorry. Oh no, I didn't go backwards. I think my slides are a bit out of order. So we have four main types of accelerating structures that I want to talk about specifically. So we already mentioned the RFQ. We're going to talk in more detail about our drift tube Linac, our CCLs, and then our SCLs. So these are really these are the cavities that actually add energy to the beam. Starting with the RFQ. So we use the RFQ as a beam injector, and we love to use the word injection in accelerators. And so many years ago, before the development of the RFQ, which happened in, actually it's pretty old technology itself, it started in the 1960s. But prior to that, and until it really became commonplace, we still use large electrostatic accelerators to get the energy of the ions up high enough to actually get them into the accelerator. You can imagine if you don't have them going fast enough, they're not going to go very far. You can't get them in very far. You can't accelerate them. So the RFQ does that for us now. And actually it's unique. It has really two functions. Well, three functions, actually. It uses electric field to accelerate the beam. It uses electric field to focus the beam, hence the radio frequency quadrupole, right? Quadrupole magnet focuses the beam, and then it also bunches the beam. We talked about this bunch structure and how very important it is. So the bunching actually starts here in the RFQ, and we do that by using 4 vanes. You get an idea of what that looks like in that center picture there. And these 4 vanes are modulated. I'm not sure you can tell, but if you look at the far right, that's a vane from a recent RFQ that we purchased from a company, RI, in Germany. And you can see how that modulation increases as you go along longitudinally. And that increases because the beam is picking up speed. So at SNS, our RFQ operates at 402.5 megahertz. And our beam energy enters in at 65 keV, like I said, right, from the ion source, and it exits at 2.5 MeV. So it's pretty good energy gain right away. And 2.5 MeV is enough energy to get it into the DTL. So the drift tube Linac, or the DTL, they're really nothing more than a series of tanks. Inside these tanks, we quite literally have tubes. And what those tubes do is actually shield the charged particle from the incorrect phase of the RF. And so they're not just dumb tubes. They actually do have magnets in them in some cases, either electromagnets or permanent magnets, and we use that to, again, these are pretty long tubes, or pretty long tanks, excuse me, and the beam starts to diverge and get off track, and so we use those to help keep the particles where they're supposed to go. And so that's exactly what I just said right there. And so these tanks are driven such that you have the same field at all the gaps. Remember, we talked about the gaps very early on in the presentation. That's where the ions are actually picking up their energy. And so here's a nice little animation that's like 20 years old, showing you that this particle is happy. He's shielded from the incorrect phase of the RF, and then when he's in the gap, he gets the correct phase and picks up speed as he goes along. So just like the RFQ, our SNS DTLs operate at 402.5 megahertz. Beam energy is 2.5 MeV at the entrance and 87 MeV at the exit. So now we talk about the CCL. So this is our last normal conducting type of RF cavity. And it's unique in that we have actually we have 3 types of cavities here. We have the accelerating cavity, then we have the coupling cavity, and we have the bridge cavity. So the incident RF wave actually enters the bridge cavity, and then it's coupled to each accelerating cell using the coupling cavities. I like to think of them just as sort of fancy waveguide, right? The RF just kind of passes through. It doesn't stick around, and it only resonates actually in the accelerating cavity. So this is kind of what that looks like. What you see at the bottom left is sort of an ancient CST movie showing the electric field, and you get an idea of the beam comes in from the left there, and the accelerating field is the positive, and so it's only in the cavity when the RF cycle is positive. So as it passes through that first cavity on the left there and makes it to the second, of course the phase would be correct there, and so on. So here we've actually increased frequency. Mainly that's because the beam has picked up enough energy now, it's moving pretty fast. So now we've doubled our frequency to 805 megahertz. We'll be 805 megahertz the rest of the way. We enter at 87 MeV, and then we exit at 186 MeV. Now we get to the point where we're really going to gain some energy, our superconducting Linac. So we operate our SCL at 2.1 K, which is about, negative, let's just call it negative 460 F. It's really cold. We use liquid helium. It's absolutely fascinating. I suggest if you're ever interested and you have another GNU conference, you should invite my counterpart. He'll tell you all about the physics of superfluids. Anyway, it's pretty fascinating stuff. So these are driven a lot like the DTLs, but they're driven in such a way so that every cell, so we have a 6-cell cavity that we use at SNS, and each cell, the RF phase is 180 degrees out. And the particles are only in the cavities when the phase is in the correct direction, right? So it's in one cavity, the field is oriented correctly. In the subsequent cavity, it's 180 out. In the next RF cycle, is you get the idea, right? So that's how the SEL cavities work. Again, we operate here at 805 megahertz, and we enter at 186, and then we come out at the very end at 1.3 giga electron volts. I should also say, I did mention this earlier, that at 1.3 giga electron volts, our hydrogen ion is moving at about 90% of the speed of light. So it's moving pretty fast. So we talked a little bit now, or previously, about the cavities. Well, how is it we actually get the power? So we have what we call high power RF transmitters, all right, and we generate megawatts of RF. Our gain from what you see, the low-level RF signal there on the left to the cavity on the right is about 90 dB, and that's multi-stage, as you can imagine. The first stage, we have a very simple solid-state amplifier. It takes that low-level RF signal in, amplifies it by about 30 dB. The output of that amplifier then feeds a klystron or a tube, mainly klystrons, and we'll talk about those here in a couple slides. They're the workhorses, right? They really give us a lot of gain, 60 dB, and they're the ones that we have output in the kilowatts up to the megawatt level. So just like the accelerator, we can divide our high-power systems up. All right, we have 3 main systems. The one for the RFQ and DTL is effectively the same, and those are, you can see the klystron associated with those. That's the big silver klystron you see there. Those are 402.5 megahertz, like I mentioned, and 2.5 megawatt peak power. And I should also mention that we pulse the system. I mentioned that earlier. Our pulses are 1.5 milliseconds wide, so it's a pretty wide pulse, almost CW, almost considered CW anyway. It's 60 hertz. Then we have 805 megahertz, 5 megawatt klystrons in the CCL. You can imagine the normal conducting takes a lot of power to get energy into the beam. SCL, not so much, right? Superconducting is a lot more efficient. So there we only need 500 to 700 kilowatts, or 550, excuse me, to 700 kilowatts of peak output power to get the energy we need at that point in the accelerator. And those are the little bitty, as we call them, the little bitty red klystrons there on the right-hand side. All right, so a little bit about klystrons for those of you who don't know. So they're a tube amplifier. I guess that's no shock. They, of course, use a stream of electrons. We modulate that stream of electrons using RF cavities. The way it works is we pulse the cathode. So the cathode is a good electron emitter. We heat the cathode up. We then pulse it with a large negative DC voltage. That creates that beam. And the very first cavity, and you can see there's a picture there of klystron halved and laid on its side, right? So the first cavity, we tickle in a little bitty RF signals. It's usually on resonance. And then that starts bunching the beam. And as those beam bunches pass the subsequent cavities, they actually introduce, or couple rather, a wall current, right, that mirrors the actual pulses as they go by. That wall current then sets up a voltage across the gap. We talked about gaps earlier. That acts on the subsequent electrons and makes the bunching even more intense. So ultimately what you end up with is almost an impulse. And you can tell, if you can follow that electron diagram there at the bottom of the little movie, you can tell that at the very end, the voltages in those cavities are so high, they're actually turning the electrons around and stopping them. So you have an electron beam traveling at about 60% of the speed of light or better, and suddenly you put the brakes on, you're going to get a lot of energy out of that beam. And that is how we use it to make high power RF. So now a little bit about the system that controls it. So I've already mentioned low-level RF. So low-level RF is actually what we use to close the loop between the accelerating cavity and the high-power RF system. It's got pretty good regulation, 1% amplitude and 1% phase. Just very briefly, what you can see here is actual operator screen. So this is what the operators use to control the cavities in the control room at SNS. And then, of course, the hardware. We use micro TCA, for those of you in the room who are familiar, and FPGAs to control this. I would be hard-pressed to tell you the exact model of FPGA, but just note that that's how it's actually operated. So the low-level system, the way it works is it compares the amplitude and phase of the cavity to a reference signal. It then calculates an error, right, and it corrects for that error. And the way it works is, so we sample it first at the fundamental, either 402 or 805. We down-convert that to 50 megahertz. Then the 50 megahertz signal is corrected, right? It's the amplitude's changed, the phase is shifted, and then it starts amplifying it. So the output of what we call the field control module then gets up-converted back to the fundamental. The fundamental is amplified using that 90 dB amplifier we just talked about, and ultimately provides power to the cavity. And there is your control loop for the cavities. Also, it does provide some protection functions, just as an aside there. So let's talk a little bit about the ring, and then we'll come towards to the end of the talk. So I mentioned earlier we have 4 tetro-based RF stations there in the ring. We have 2 that operate our ring fundamental frequency of 1 megahertz, and then we have 2 that operate at 2 megahertz. And their primary purpose, as we're accumulating these protons, is to keep that proton bunch tight, and then the 2 megahertz actually beats it down. So as they want to spread apart, longitudinally and transversely, the ring RF works against that to keep them tightly bunched. So now we're coming to the end. We've made it all the way through Accelerator. We're bopping along at 90% of the speed of light, and we're going to start accumulating protons. So how does that work? So I mentioned earlier, we actually accelerate a hydrogen ion. The ions are then injected, there's that word injection again, into the ring, where they strike a diamond foil. And that diamond foil quite literally strips the excess electrons off of the hydrogen ion, and it becomes a proton. You can tell here we actually have 3 beams that come out of injection. We have H-, sometimes we just miss. We have H-0, where we basically it's a regular, for lack of a better word, hydrogen atom, and then we have the actual proton that we start accumulating around the ring. We dump these other 2 beams. Just as an aside, we are looking at other uses. They are actually relatively high power, not megawatt level power like the proton beam, but kilowatt level power that we could use for other science. So we start accumulating these protons with a multi-term process. I mentioned the ring RF. So basically what happens is these pulses enter, and it takes the period of 1 megahertz to make it around the ring. And this is one of the reasons why we use H-0. So you can imagine you start accumulating a bunch of protons, you start getting these space charge effects. If we stripped the electron any earlier, we would have a lot of trouble getting more particles into the ring. So keeping it H-0 actually helps combat that, since the light charges attract each other. And the other reason we use hydrogen is obviously it's a great source of protons, right? It's a single proton. It's very easy to get a proton from a hydrogen atom. So I didn't mention this very early on in the talk, but let's talk just briefly about the actual pulse, the 1 millisecond, 1.5 millisecond wide RF pulse, and what's contained in that. So in actuality, our 1 millisecond wide, so we have a 1.5 millisecond wide RF pulse, and in that we have a 1 millisecond beam pulse. That 1 millisecond beam pulse actually consists of a bunch of mini pulses that you see here. And this is the gap I was talking about. This is what the RFQ starts setting up, then the MEBIT cleans up, and so we get this nice pulse train coming down the Linac. And it's long enough that if you grab the first pulse and you started walking, you would be to Nashville by the time the last pulse came out of the ion source. So it's literally that long. So what you can see here on the time structure, each pulse period is 945 nanoseconds. That's the same, that's the period of 1 megahertz, right? So quite literally what happens is a single pulse at a time goes around the ring, and you get an idea graphically of that accumulation there in the bottom right. And ultimately what we do is we compress it all the way down to about 700 nanoseconds, and that's what actually hits the target. And inside that compressed pulse is about 10 to the 14 protons. Right now the figure is 1.6, 10 to the 14. Ultimately, when we're finished upgrading the SNS, it'll be more like 2.3, 10 to the 14, so a lot of protons. In terms of current, we have measured up to 75, depending on the shape of the pulse, we have measured up to 75 amps peak, so it's actually quite a lot of current moving, at 90% of the speed of light, so a lot of kinetic energy there. So what do we do with it? So we take that that proton pulse, and we strike a liquid mercury target. It's liquid because things get hot, and it's easier to cool liquid mercury than really anything else. And so on an atomic level, this is more or less what happens. The proton strikes the mercury atom, makes it unstable, and then that mercury atom gives off 5 neutrons and 1 proton. So it remains mercury. And basically, scientists, and I don't have much to do with this end of it, so apologies for being a bit ignorant of exactly what happens on the far end. But basically, SNS is a material science facility, and the accelerator and the RF is more or less a utility. And this is really the end goal right here. We have material science from scientists from all over the world using neutrons to probe matter. So this is the end. RF-based acceleration is really the most efficient way to add energy to a charged particle beam. SNS, we have 131 RF systems that do that. They pulse 5.2 million times a day. And I'll just say thank you for the invitation. I'm happy to take any questions you might have.
Do you have to have your own power station to run this thing?
No, that's a good question. We do have, we do not have our own power station. We do have our own switch yard. ORNL in general, actually, I don't know if you went on the tour, but there's the Bull Run steam plant. If you are coming in via Solway, which is the way you would come from Knoxville, you'll notice a coal-fired power plant up to the right. That's basically there to support ORNL and I believe the Y-12 National Security Complex right next door. So short answer is kind of.
What kind of sensing you have to have in the loop just to sort of know that things are going as expected?
So your question is about sensing, is that what you said?
Right, since it's a closed system in operation,
Sure.
I assume.
Sure, so we actually have, so specifically for our RF, we have, basically we measure power, right? We look for arc detection, just light, right? We have fiber optics that look at certain points, especially the high power side. We look for arcs, we monitor vacuum. Obviously we have to have the entire accelerator under vacuum. As far as the beam goes and making sure it's on track, we have beam position monitors. We have radiation detectors, and so these beam position monitors actually they give you a sort of a two-dimensional view of the beam spread, so you can look at it and you can tell basically is it the spread that you're looking for. And then the radiation, like if we have beam that strikes a place it doesn't need, it's not supposed to strike, right? It'll give off radiation, and whenever that happens, it will shut off the accelerator momentarily, but it does stop it.